Just watch this.
What did I tell you? 88 miles per hour!
All right, that was a little scene from Back to the Future. We're going to talk velocity, and hopefully you will be excited as Doc was in there with the 88 miles per hour. I think you'll probably be that excited when you're done with this video as we talk a little bit of velocity. So let's get this rolling. So velocity is a rate of change. So a lot of times when we've seen graphs, we've been looking at time versus distance, but be careful. We're going to look at time versus velocity now. So anything with a per, feet per second, miles per hour, kilometers per whatever, minute. Anything with a per is a rate of change of velocity. So think about this. Think about Mr. Kelly. He loves to ride Segway. Here he is. He actually does some extreme Segway. I'll throw a little picture of extreme Segway in there, off-roading stuff. This is him riding a Segway. This is his velocity over time. So when I think about this rate of change, what's happening? Here his velocity is increasing. So he's picking up speed. He's cruising. Maybe he cruises to 10. And what is that? That would be 10 feet per second. So he's got an increase in velocity. What happens? He's got this constant flat rate. He levels it out. Maybe he's going cruising. He's pretty happy with 10 feet per second. So this is like a constant right here. So it's kind of weird. Then what happens? He actually slows down his velocity to another constant. Then what happens here? He is slowing down his velocity to the point of what? What does this mean now? This actually means he has no velocity. It's a zero velocity. Then what happens? He's actually what? He's actually stopped and turned around. He's going in the other direction. So he's increasing negatively. So he actually turned around and started going the other way. Then what happens? He started to slow back down until this. And then he increased his velocity to a constant and then slowed back down to a zero. So this is when he has no velocity. These zeros are very important. And then these points, these are like turning. No, that's not turning. These are the turning points. The zeros are the turning points. And when he went left or right. Excellent. So that's a quick thing on velocity. What is speed then? I mean, sometimes we use them interchangeably. Velocity has direction. Like you can go right, you can go left, up, down, whatever. Velocity has no direction. It's just the absolute value. So if I didn't care about the direction he was going and I just wanted a speed graph, what would happen? You just absolute value the velocity. So this negative part wouldn't exist anymore. It would be absolute value. It would look something like this would be a speed graph. So it's the absolute value of velocity. Awesome. Pretty cool. So moving on. To be good at this section, we really dimensional analysis will help us. So we've kind of been looking at this when we were doing radians to degrees. Can we convert things? Yeah, 3 miles is how many inches? So if I do this, this is not a rate of change. I'm just converting 3 miles into inches. So you got to know a couple things. We got to know a mile is 5,280 feet. So I put a little conversion in there. So the whole idea of this, we are converting miles to feet. If miles is technically on top, that's like 3 over 1. Miles is on bottom, feet's on top, so feet will be on bottom here. 1 foot is what? It is 12 inches. So the whole idea of this when we're done is the miles cancel the miles, the feet cancel the feet, and I've magically turned this into inches. So when I multiply it all out, it's really nice. You just multiply across the top, divide anything that's on the bottom. So this is really just 3 times 5,280 times 12. That's going to get me my inches, and it's a lot of inches. 190,000. Can I fit that in there? In 80. Don't forget the 80. So there it is in inches. So yeah, 3 miles is a lot of inches right there. Excellent. So we're going to do a lot of changing rates of change. So when I write this, this is 45 kilometers for every 1 hour. So it's a rate of change. If I want to change this bad boy into meters per second, just start changing it. Kilometers, we got to change into meters. So what do we know about kilometers? 1 kilometer is 1,000 meters. So I'm coolio there. That is good to go. My kilometers are in meters. I also need to get the seconds, so now I got to change the hours. So hours was on bottom. What do you got to do? You got to put the hours on top to get them to cancel. What does an hour turn into? Turns into 60 minutes. But I want to get to seconds, so what do I got to do? Minutes is on bottom, so I better put minutes on top. That is 60 seconds. So you know you're right when everything cancels out. Like your kilometers are canceling, your hours, where are they going to cancel? They are going to cancel here. Your minutes are canceling out, and what am I left with? Just meters and seconds. So that's exactly what I wanted. Go ahead and multiply this bad boy out. Let's go slide him over here so we can see what's going on. Just multiply across the top, so it's 45 times that 1,000. And these are just ones. You can go times 1, divide by 1 if you want, but then we'll divide by 60, divide by 60. And this should give us our meters per second, 12.5. So hopefully you've done a little bit of this. Maybe you're taking some chemistry or something. You do some of that. This one may be a little new for you, though. What about revolutions? 7 revolutions every 3 minutes. So I want to convert this into radians per second. This is where we're going. This is the direction we're heading. So it's the same idea. What do I know about revolutions? Well, a revolution, not in like a war kind of sense, but in a circle kind of sense. One revolution is what? Is how many degrees? If you do one revolution, you do 360 degrees. So we've kind of been playing with this idea past couple packets here. It's 360 degrees, so one revolution. But I don't want degrees. I want radians. We're not going to do degrees on this. We're going to do one revolution is what? It is 2 pi radians, or 2 pi rad. So instead of doing a 360, you do a 2 pi. That's great. So now I can convert revolutions to radians. I can still do my minutes per second. Just make sure minutes is on top. 60 seconds is on bottom. Let's double check everything cancels. My revolutions canceled. My minutes canceled. I'm left with radians per second. So here when you multiply it out, I'm cool with either way. You can say 7 times 2 pi is what? It's 14 pi. And then 3 times 60 is 180. This is a great answer. This is a fine answer. This is radians per second. If you want to make it a decimal, I got no problem with that. You can use 3.14. Probably should reduce the 14 really. We should probably say it's 7 over 90. That would be a little bit cleaner. So that would be the most exact answer. Ooh, that's a terrible looking radians per second. 7 pi over 90. If you want to decimify it, go ahead and decimify. That's dimensional analysis. Why do we need that? Well, we're going to start talking velocity. So I like to think about this. We got a new kind of velocity here. We're going to think about linear velocity. We've done this forever. Distance equals rate times time. So let's say you've got some little dude here running on the track. Maybe he's running this way. So this guy's got some kind of velocity that he runs with. Maybe he runs, I don't know, 10 feet per second. That's how fast he's running on the track. So no problem. He's just cruising. He's just running. So this is our normal velocity. This is called linear velocity. And it comes off this classic formula here. You know, if you want to solve for the rate, what is this guy's rate? It is just distance over time. He's going 10 feet per second. So we kind of change that to a v, and it is just distance over time. That's his velocity. So no problem. We're used to that. We've been doing that. Cars do it. All kinds of things have that velocity. Not a problem. What's new for us maybe, unless you're in physics, is this angular velocity. And so it happens at this part of the track. So all of a sudden he hits the curvy part, you know. So what happens when he hits the curvy part? Well, he still has a linear velocity, right? Like he's still running, and he's still running 10 feet per second. So just because you change your direction or hit a curve, if he maintains that velocity, it's the same. So he still has a linear velocity. It's still this pushing him 10 feet per second. But now we've picked up something new. Think of this half track like a circle. So if it was a circle from here to, let's say he's here. Ooh, that's terrible. He actually now picks up the way he goes across this circle. So if this is angle theta, we're looking at how quickly he turns the circle. So let's just look at a circle. If I'm at point A and I'm on a circle and I run and I'm running around the circle to here, yeah, that linear velocity, but now as quickly as I run is changing this angle theta. So the faster I run my linear velocity is actually going to affect my angular velocity. So this is new. We're going to say how fast do things spin, essentially. How fast do they go in a circle? So angular velocity is this. So it's W equals theta over time, where that W is the angular velocity. So W means angular velocity. Theta is the angle we're looking at, and we're just changing it over time. So maybe he goes, well, let's do a problem. Let's see what it could look like. Awesome. Well, I'm cruising. I feel like my velocity is pretty fast on this. You may need to pause it, slow me down. Let's think about horse training. Have you ever seen them train a horse? They canter or whatever those horses do. They put them in a circle and they run them around the circle and train them to do whatever they got to do. So think about this horse. Let's say the horse makes 3 revolutions every minute. Well, that's great. That's awesome. We're going to use this idea of angular velocity to find out linear velocity. So if his pin is 15 meters radius, and he's running around from like point A to point B. So from A to B, this is changing. So how is it changing? Well, it makes 3 revolutions every minute. So if I want to use this formula, if I want to find the angular velocity, I just need to know what this theta is. Well, what is this theta? It's 3 revolutions. What are revolutions? It's got to be, theta has got to be in pi, in radians. So it's 3 revolutions at 2 pi. His theta is actually 6 pi. How often? What's the time? Every minute. So he has a angular velocity of 6 pi radian every 1 minute. So angular velocity is always going to be in radians per some unit of time. That's it. So all we're really doing is change revolutions to radians. That's how fast this is going. He does, and it makes sense. He does 6 pi every minute. He does 3 revolutions. That's 6 pi. That's how fast his angular velocity is. So you're like, that's great. That doesn't mean much to me. But I can use that to find his linear velocity with this fancy formula. Now we're not going to take time to derive this. We're gonna use it. Velocity equals the radius times the angular velocity. This is why angular velocity is so cool. I want to know his linear velocity. All you have to do is times it by the radius. Boom. It's 15. What's that? His angular velocity we said was 6 pi. You can put some people like to put the radians per minute in there, but that's it. It's 15 times 6 pi. So what's his linear velocity? Well, it's just going to be 90 pi. Now, what is the you got to label everything. I think the trickiest part is just labeling it. What's he's going 90 pi what? Well, it goes automatically to the unit that the radius is in. So it's in meters. This is now meters, and the time stays the same, meters per minute. Excellent. We could have easily gone back here and done 60 seconds. It can be per whatever, but whatever you're in, it just follows through. So the time will stay the same. Whatever this is in is going to give you the label there. That's really the whole section. It gets a little bit trickier, got some word problems, but that really is it in a nutshell. Alright, let's see if we can put this together to a classic angular velocity. Let's take a look at this fan. If you guys don't know, I'm a huge Bengals fan. Do you get it? It's a Bengals fan. Alright, anyway, let's take a look at the Bengals helmet. Let's pretend that you are a point at the end of this on this Bengals helmet right here. So I want to know how fast would this tip of the fan be going. So it's going in a circle. So it's got that angular velocity, plus it's got its linear velocity. I want to know how fast is it going. Well, I brought my formulas over here. 9 revolutions per minute. So let's find the angular velocity. If I said, what's the angular velocity of that point on the end? Well, it'd just be what? 9 revolutions per minute. So remember, 9 revolutions, 9 times 2 is 18 pi. I'm going 18 pi every 1 minute. There is my angular velocity. Awesome. What do I want to do with that? I want to change it into linear velocity. So what am I going to do? How fast is that? Like if this point fell off, what would it shoot off at? Pew! It would be what? It would be 3 feet, and then that was just 18 pi. My linear velocity is just what? 54 pi. Help me label this. I am now in what? I am now in feet per minute. Fantastic. So I use the angular velocity to get to my linear velocity. Some people like this little shortcut over here. The formulas are great, and I'm going to give them to you on mastery checks and test. But here's really all we're doing. If I give you revolutions and I want angular velocity, what are you doing? You are timesing it by 2. So to go to revolutions to angular velocity, you times by 2. To go to angular velocity to linear velocity, what do? You times it by the radius. That's it, man. So it's not crazy crazy hard. This is how you go from 1 to 1. How do I go back? Let's pretend I give you linear velocity. You just divide by the radius, you'll have angular velocity. If I give you angular velocity and you want to know my revolutions, what do? You divide by 2 pi. This is a great shortcut. I think I gave you part of this, just fill it in. You may want to use that for some of these word problems to help you through it. Fantastic. We are cruising. I want to look at one more example, then I got some problems for you to try, and then I'll put up the answers and see how you did. But let's look at this one together. Let's say Mr. Sullivan loves merry-go-rounds. So he's on his favorite merry-go-round, and he usually rides the horse on the outside. And let's say that horse is 12 feet away. So if this merry-go-round is going around and it makes 5 revolutions per minute, what is Mr. Sullivan's, let's say, angular velocity? It would just be what? If I got 5 revolutions, his angular velocity, I'm going to use the shortcut here, is just 10 pi. You times it by 2 pi, and what am I in? I am actually in radians per minute. So again, make sure it's radians per, always radians per minute. Can I find Mr. Sullivan's linear velocity? Sure, his linear velocity would be times it by the radius. So I'm going to times it by 12. So it's going to be 120 pi. And now what am I in? I am now in feet per minute. Awesome. Problem is, I want to know his miles per hour, because when you say feet per minute, that's hard for my brain to think about. But when you say miles per hour, I can think about my car. I'm pretty cool with that. So it makes more sense to me. So what do I have to do? There comes that dimensional analysis. Woo! I knew we'd use it. Right now I'm at 120 pi feet per minute. Want to convert this bad boy to miles per hour, so let's go ahead and do that. I'm going to convert what? I think we said 5,280 feet is 1 mile. And minute, I want to take minute to hour, so 60 minutes on top will give me 1 hour. So really, how fast is Mr. Sullivan going on the carousel? He's going 120, and I'm definitely going to go decimal now. I'm just going to use the pi button. 3.14 is cool. I'm going to decimify this, so multiply it out. 120 pi times 60, then I'm going to divide it by that 5,280. This should be my miles per hour. Looks like about 4.28 miles per hour. So there he is. He is cruising on his carousel. Awesome. Let's say he talks his good friend Mr. Kelly into riding with him, but Mr. Kelly has to take the horse on the inside here, so he's a little bit closer. Let's say Mr. Kelly is 8 feet away from the center of this. What do you notice about these two guys? Besides they're adorable riding the carousel together, what do you notice? What's the same about them? Well, they're both on the carousel. They're both rotating. What do they both have in common? Well, as they spin around, they both have the same what? They both have the same angular velocity. They are both going, if that's Sullivan, here's Kelly over here. He is also going 10 pi rad per minute. Because he's on the same line here, so he has the same angular velocity. What's different though? Well, the radius is not as big. So the only difference here is Mr. Kelly's now got a linear velocity of 80 pi feet per second versus that 120. So the farther you get out on the carousel, the actual faster you're going. And maybe you've noticed this. If you're close on a carousel, you don't go as fast. So if you want to go faster, you go, I don't know. So you can definitely have the same angular velocity. And in fact, you can also have the same linear velocity in different cases. Pretty cool, huh? All right, so there was using the shortcut. Here are 3 problems. I wrote them out for you. If you want to try them, pause it, try it. Whatever you do, make sure you see the answers and definitely watch the clip at the end because I think it's pretty awesome. But if you want to go through with me, I'm going to solve them right now. So you may want to pause and read them though. Maybe read through and see what we're talking about, see what's going on. Go ahead and pause, read them. All right, so hopefully you read that. This is one where I think I'm going to use the formula. So I like to write down what they give me. They give me a diameter of 2 yards, so I'm going to say the radius is 1 yard. I usually like to know radius. And what else do they give me? So they give me the linear speed, so they give me the velocity. I mean, speed is velocity, it's just without direction, as 100 feet per second. And you want to find the angular velocity in radians per second. So I'm looking for W. And I also got to find the number of revolutions. So once we get that, we'll try to get a revolution. So what's the formula that ties this all together? I think it's going to be, well, we only have 2 formulas. So it's either W equals theta over T or this one. And this has got everything we could want. It's got the V, it's got the R, it's got the W. One quick thing that I noticed here though, when you use this formula, you have to be in the same units. So the radius is in yards, the velocity is in feet. Let's just change this. 1 yard is really what? 3 feet. So if they're in the formula, you got to be consistent here. So make sure you do a little dimensional analysis to clear that up. So the linear velocity is 100 feet per second. The radius is 3 feet. The angular velocity I do not know. So if I solve this, what do I get? It looks like my angular velocity is 33.3 repeating. And what is angular velocity in? It's always in radians per, boom, this is in time, was in seconds, so this will be in seconds. Is that what I'm looking for? Yes. There we go. I mean, you could left it 100 over 3 radians per second. Aha, what is the revolutions per minute? Well, if that's, all right, so we got 33.3 radians per second. That's just, 33.3 was that 100 divided by 3. So I made a decimal here, but I think over here I'm going to want it as its fraction because what is this? This is radians over seconds. So it's like this, 100 radians every 3 seconds. So can I convert that into revolutions in a minute? Sure, I can convert that. Let's go to revolutions. I got radians here. I want revolutions. What do I got to do? I got to say 2 pi radians, that's a circle, is 1 revolution. And then I got to convert my seconds. 60 seconds is 1 minute. So now I'm just doing a little conversion here. I want to multiply this out so I can see what's going on here. Let me clear that bad boy out. So on top I've got 100. I'm timesing it by the 60 seconds. On bottom I'm dividing by 3 and dividing by. Be careful here. When you do the 2 pi, you got to put it in parentheses. You're dividing by all of that 2 pi. If you don't, it's going to divide it by 2, then times it by pi. It's going to mess you up. So make sure you put the parentheses there. And it looks like I am doing what? 318.3. So 318.3. What was that? That should be revolutions per minute. Excellent. So a little dimensional analysis there and a little formula. That was a really fun one. I enjoyed that. Awesome. Moving on. I forgot to talk about this. I love these old-timey bikes. Look how cool. Can you imagine riding one of these bikes right here? Like the huge front tire. Plus they make for great problems like this one right here. Check out this lady though on her old-timey bike. This would be the first epic fail picture, I think. You know, the old camera. They got the epic fail. That's a bummer for her. So another bike problem. This time the front wheel is different than the back wheel. So we've got this big front wheel and the small back wheel, or vice versa. I don't know what the front and back is. And I got this going on through what angle? So I'm having a hard time with this. The front tire is 40. And is that diameter? So let's say it's 20. The radius is 20. The back tire has a diameter of 60, so we're going to say this is 30. So this is my bike. And if it's going, I want to know what is the angle of radians does the front wheel turn if the back wheel turns 15 radians. So if this one turns 15 radians, how much does this one turn? Well, the little one's going to turn more than the big one. What do you notice about this? This is supposed to be a bike. I'm scared to draw it, but this bike has to be what? Well, it's traveling on the ground. It has to have the same what? Not angular velocity. These spin different speeds, but they have to have the same linear velocity. It's got to be the same, or else you would look like that girl over there. The bike has to have one linear velocity. So as you bike, you have a linear velocity. So I think I'm going to go formula again on this one. If we're talking about linear velocity, we're talking about this. The thing we know about this is v is the same in both of them. I don't know what v is, but it's the same. So what I would do is say, okay, this angular velocity of the back wheel, 15 radians. So we know the back wheel goes 15 radians, and it has a radius of 30. So that's the back wheel. Has to equal the front wheel, which is 20, and we don't know the radians. So that's going to be my w. So the units of time doesn't really matter here. We can just multiply this out and just solve for w here. I mean, you could pretend it's a minute, a second. I don't really care. It's all going to work out here. So if I multiply this out, what am I going to get? I'm going to get 450 equals 20w. Boom, divide by 20, divide by 20. What is my angular velocity, or what are my radians? In this case, let's go ahead and get it. We're going to do 450 divided by 20. Should be 22.5 radians. And then I think, does it make sense? Always take a second, doesn't make sense. Yeah, if the back one does 15 radians, so don't freak out when you see 15 radians. 15 radians, it just doesn't have a pi in it. If you want to think more of revolutions, you could divide it by 2 pi and see what you get. But it's just going 15 radians, so the small one's got to spend more. 22.5 radians seems legit. Woo, good answer. So sometimes I'm going to throw some tricks at you where you got to think about, oh yeah, they got the same linear velocity. I can do the formula. I'm good to go. All right, the finale here, the last one. Again, pause and try it if you like. This is another fail picture. I hope that's photoshopped, or that dude is going to be hurting. A couple things here. So again, I'm mixing up. I'm going to give you circumference. Remember, circumference is what? I always remember this. Cherry pie delicious. Apple pie R2. Cherry pie is delicious. Apple pie R2. We're not going to need area for anything, so forget about area. But that helps remember circumference. And circumference is 87 inches. So all we're doing here is saying, hey, you're going to have to do a little work to get to that radius. The angular speed, or angular velocity, is 20 radians per second. And you're trying to find w. I don't know the linear velocity. This is one. Let's see if we can use the shortcut on this one. Can we use the shortcut? My goal is this. I have the angular velocity. So if I have angular velocity is 20, all I got to do is times it by the radius, which is what? Well, let's find the radius. Instead of diameter, what can we use? Diameter is what? 2 radiuses? 2 radiuses or 2 radii? 2 radii, I think. So if I want to find this, I'm going to divide by 2 pi. Divide this by 2 pi. So my radius is really 87 over 2 pi. Not very friendly radius there, but that's okay. Again, if you want to make a decimal, I'm cool with that. So all I'm going to do is take the angular velocity, w, times it by the radius. That's going to give me my linear velocity. Alright, here we go. Let's multiply these out, and it looks like what we get 1,740, I'm guessing, over 2 pi. And you can make this a decimal if you want, but I'm going to leave it as a exact value here. And what are we in here? So we're looking at what? I'm looking at what was my radius in. It was in inches, so this is going to be the inches per, and what was our time? Our time was second. So I'm in inches per second as my linear velocity. Kind of weird. In fact, they want me to find miles per hour. So let's go ahead and convert this bad boy to miles per hour. So if I've got that 1,740 inches every 2 pi seconds, let's convert this over to miles per hour. So we're looking at what? 12 inches here is 1 foot. And then make sure feet is on bottom to keep them opposite. So we're looking at 5,280 feet. That is 1 mile. Awesome. And that's good, I'm in miles, but I also need to go to hours, so let's change the seconds. It was on bottom, so I need to say, hey, 60 seconds is 1 minute. And then I got to change my minutes into hours, so that would be 1 hour. So hopefully if I did everything right, it's all going to cancel out. So I got inches, cancel inches, feet, cancel feet, miles is what I'm looking for, second, cancel second, minute cancels minute. I am in miles per hour. Let's go ahead and finish this bad boy out and multiply it all out. So I've got 1,740 across the top. I'm going to times it by 60, times it by 60, divide by, remember, be careful with that 2 pi. You got to put in parentheses the whole thing. Hate to see you missing a master check or something. Divide by the 2 pi, divide by 12, divide by 5,280. Is that it? That should be everything. So multiply it out. Looks like I'm going about 15.73 miles per hour. So that's how fast the bicycle is going, given all that information up there. Awesome. That is it. This next clip is a great clip. I went ahead and added some angular and linear velocity to a music video that was shot. I actually think it's from Sullivan's Family Reunion. I think they shot this one year. So enjoy the video. Good luck on the match check. Peace out.